Okay, let's get started. To summarize, yesterday we found as we were figuring out what particle physics spectrum to expect, when we looked at m equals 0, we saw j equals 1 and j equals 2. J equals 2 was so constrained in terms of its interactions that it implies general relativity, and that already implies the end of particle physics, known as the Planck scale. Above the Planck scale, for masses above the Planck scale, the classical Schwarzschild radius is already bigger than the Compton wavelength. And that implies that the particle is not a particle, it's not a quantum particle, it's better thought of as a classical black hole. So you should study some other subject, okay? So particle physics has to somewhere be in this interval, and today our aliens take some more data, following in our tracks and our footsteps, and they find that there are masses for the W, the Z, some fermions. So finally we meet the domain of what we usually call the standard model or the Electroweak theory. And it's an interesting statement because they, like us, are gambling on what they're going to see next. How much data did they take? Well, following our steps. This is also the experimental energy. In other words, as far as they've gone in experimental energy, they keep seeing new particles. Okay. And then they stop taking the data and they're wondering what's going to happen next. Now, in condensed matter physics, as well as in particle physics, when you have the energy spectrum or even some new type of matter in quantum mechanics, no matter what, the big question is there a gap in the spectrum? If you talk to condensed matter physicists, they'll constantly be, oh, is there a gap? What's the nature of the gap? Is it this kind of gap, that kind of gap? We have the same question. Is there a gap? As far as we are taking data, as far as we're pushing up in energy and using E equals mc squared, particle, 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 it never seems to stop. The excitement does not end, okay? On long time scales. But suddenly, the question is there a gap? Well, it should be our question. We care about that. And we want to ask, what evidence do we have one way or the other that something is, whether there's a gap or there isn't? It could just be that it continues like this, but the existence of a gap meaning new particles, more and more. Or it could be that there's a gap in the sense that there's a large hierarchy like this. Okay, so we were so struck by this digital robustness of m equals 0, and indeed its relationship to gauge invariance, to gauge symmetry. Now, gauge symmetry was a function of our, the word gauge symmetry was partly by our attempt to use local quantum field theory to describe it. There's a many-to-one correspondence between theoretical description and physical reality. But this is one way of trying to describe it. And indeed, the invariant way of describing it is not gauge symmetry, but geometric concepts. The notion of gauge invariance is really a geometric concept. The notion of general coordinate invariance that we described for spin 2 is, again, of course, as we famously know, also a geometric concept, literally the geometry of space-time. The J equals 1 gauge symmetry is a subtler form of geometry associated with fiber bundles and in geometric language. Okay? But the idea that gauge symmetry, or more precisely geometry, geometric concepts, quantum geometry turns out to be forced on us once we have this. But this quantum geometry is being forced on us by the funny feature, the digital separation between massive and massless spin 1 and 2. That's what's forcing us to this geometric picture. So, what is the fate of that for these massive guys, where there's no such rationale for, at first sight, there's no such rationale for gauge symmetry or, if you like, quantum geometry? Let's see. Now it comes in related to this gap. But first, let's take some more data. We don't need it, but we might as well just see. It speeds us up a little bit to take some more data. So indeed, these the mass spectrum seems inconsistent with new symmetries that I could imagine are some sort of gauge symmetries. We simply don't see it. We don't see what we see in electromagnetism, which is some sort of charge conservation, which is at least evident. It's maybe not the gauge symmetry itself, but it's the global symmetry that is related to the gauge symmetry. We don't see that experimentally. There's no new symmetry that we can spot in this spectrum that makes us think, oh, there's some new gauge symmetry controlling these j=1 particles, the W and Z. And yet, if we look at the data, in particle physics, data consists of masses and interactions. Okay. So if we look at the masses, we see there's no sort of symmetry, there's no degeneracies beyond the ones that we expect coming from just this. Okay, J equals the electromagnetic degeneracies. We don't see anything like that. But the interactions, again, I want you to sort of think like a Gedanken experimentalist looking at data. The interactions are highly symmetric. Even the experimentalist has to say, well, when I calculate an S matrix, or when I try to fit my data to some sort of S matrix, there are two pieces. There's sort of the propagation piece, which depends on masses, and then there are some interactions which look like they're local. And I need to glue these and these together in some way to fit the data. But you can work backwards. You can take the data and you can try and strip off, oh, well, yes, I see there is something propagating there, and there, and I sort of remove all of these propagations. And I look at what interaction vertices come out, and these interactions are in fact highly symmetric, more symmetric than just demanded by electromagnetic gauge invariance. And in fact, they seem to be consistent with new gauge symmetry. In some sense, the puzzle posed experimentally by Electroweak data, even historically, is that the data actually, if you sort of try and split the theory up into interactions and mass terms or propagation, the interactions seem to be, what happens at interactions are things that happen at the point. The point-like interactions seem to be consistent with a gauge symmetry, which is even evident to the experimentalist eye. It's not some theoretical way of writing things. There's experimental data that is really yelling out, something is very symmetric, it's more symmetric than just U1 electromagnetism. And yet, everything to do with long-range propagation, or any kind of non-local propagation, is highly inconsistent with any of these symmetries. So the one sector seems to have interactions which are symmetric and propagation which is non-symmetric. We'll review that in 1 second. Okay. And so we have to ask, why is that going on? The other aspect is to think about what this gap would mean if there is a gap. Okay? So a gap, and we get a hint about what this puzzle in the data could be about. A gap implies that we can extrapolate whatever this sector is with just this many particles. We can extrapolate, if there's a gap, it means we can extrapolate the theory consistently to rather high energies. Okay? So we can extrapolate to energies which are much bigger than m. Okay. Now, since in relativity m looks like this, m appears like this in the energy, if the energies are much bigger than m, then it looks like these become, at high energies, masses become irrelevant. You would expect that the theory should somehow forget the fact that there are masses. If indeed there's a gap and you're operating at energies here, then surely these masses must look like almost nothing. Okay? That's what you'd expect. But in that case, but then J equals 1 W's have, okay, from the vantage point of energies of this magnitude, even the W boson and the Z boson would be approximately massless. And so, of course, you know all sorts of subtleties which we can review, but naively you would say, oh gosh, then even the W's and Z's, if you can extrapolate the high energies, the W's and Z's are effectively massless. Massless J equals 1 means that we have to have gauge symmetry as the description of that kind of physics, okay, of those particles and their interactions. And that implies new gauge symmetry. But it should be a gauge symmetry that only becomes important, only gains significance, it would appear, as you go to high energies and you effectively become massless. And so the fact that the interactions, you know, this mass spectrum, if I just say, from the vantage point here, all of these things just look like this. If I'm sitting up here, all of this can be summarized like this. Okay? I don't see this. It's effectively zero. In which case, even the mass spectrum becomes symmetric. The interactions are already surprisingly, I want to show you it is a surprise. You can take it for granted because you read the textbooks, but in some sense there's some information here. We want to gauge what it is. The interactions are experimentally highly symmetric, more symmetric than just U1 electromagnetism. At very high energies, I can forget the masses of any particles I've seen, in which case this is trivially symmetric, in which case everything is very symmetric, and it seems to be consistent with a new gauge theory, which we want to address, a new gauge theory, bigger and better than just U1 electromagnetism. And all of that suddenly fits as long as there's a gap. Okay? So, indeed, there would be no reason to have new gauge symmetries or anything if you have simply massive particles and there was no added structure. But as soon as you say that there's a gap from the particles that we've seen, then all of a sudden it makes sense that there should be new gauge symmetry, and at energies where you can forget the masses, it should, however, still show itself in these gauge interactions, and the interactions being highly symmetric. So we started to smell that maybe there's a gap, but we need to figure out the whole plot. And why is that? Even naively, we should be worried about such an extrapolation that says that just because we have j equals 1, we have new gauge symmetry. Seemingly, the n to 0 limit, is subtle, or it must be subtle, because the 3 degrees of freedom of a massive spin 1 particle has to somehow go to 2 degrees of freedom. So there must be something going on. You cannot just quickly say, oh, you cannot just look at this formula and say masses become irrelevant at high energies, and therefore we get gauge theory, and so on. There's clearly something going on. It's odd because it seems that very naive gambling, as long as I'm turning on energy, I keep seeing new things. Life is always exciting, but we seem to have come to a point where there is some information pointing to consistency with the gap. That doesn't mean that it proves that there is a gap, but suddenly for the first time there is some hint that there is some sort of a gap to expect. Okay? So we have to address that. We also have to address whether, maybe this statement I'm making here is not immediately apparent to you. Again, from the textbooks you know what I'm saying, but that's as a theorist. You might not say, to what extent is the data telling me this statement here? Okay. Because data does not easily look at gauge symmetry and stuff like that in the theorists see. There's some invariance there. Okay, let's see how we should go about thinking of this. So we want to think about the let's think in general in quantum field theory about extrapolatability. Okay. To high energies in quantum field theory. And as long as we're talking about point particles, or effectively point particles being extrapolated to high energies, and they keep looking like point particles even though the wavelengths are now getting small, that's what I mean by extrapolating. You don't suddenly discover that the point particle is actually a banana or something like that. Right? So the extrapolatability to high energies is, of course, what we normally call renormalizability. Sometimes there's a sense of renormalizability. I mean precisely renormalizability. There is something that we think about. Renormalizability originally was intended to say that the theory could be extrapolated to infinite energy, to arbitrarily high energies. Now we know that that's a subtler story, which I'll review a little later. But we do mean that renormalizability means that the theory can at least be extrapolated to extremely high energies, in a sense. We can make it precise later. Okay? So let's quickly just go, I don't want to go through all the subtleties, which you will go through in the course of your education or have already gone through. But we know this, that if you have a coupling constant, that's what I mean by G, a coupling constant whose canonical, and the other fine print when I talk about extrapolatability is that the particles are weakly interacting, meaning I can still think perturbatively. Okay? This concept generalizes at strong coupling, but let's keep it simple. I'm just telling you the fine print. The fine print is point particles that extrapolate, remain point particles, and are weakly coupled. And then we think that is what the meaning of renormalizability is. And in weak coupling, you can use some sort of dimensional analysis and basically get the right answers. So what I mean by these square brackets is the scale dimension of a coupling. If the scale dimension of the couplings of a theory are not negative, then that's what we mean by renormalizable. Okay, or that turns out to give us renormalizability. And so example, let's just do the case that's most familiar, when, like in QED, where the couplings are dimensionless, and then we have an expansion in powers of this weak coupling, as long as the coupling is weak, we can do this expansion. Now, there are all sorts of wonderful subtleties, divergences, this, that, the other. To me, this is like learning that there's in calculus, this is a function, this is the slope. Everybody can plainly see what the concept of slope is, but there are all these technical details, limit as h goes to 0, f of x plus h minus f of x over h. All this technical thing, oh my gosh, I'm dividing by 0 in this limit, there's divergences. Who cares? Because if you understood it correctly, you end up seeing it like this. That's how you should end up understanding renormalizability ultimately, that well, which is a subject related to the renormalization group and so on. To get the grand view, which tells you every move to make instinctively, as opposed to following the textbooks in every possible way, to have as instinctive a view of renormalizability and renormalization and renormalization group as you do of calculus should be a goal, right? But ultimately, these are all the subtleties. In the end, you can do this expansion and it works. There are some subtleties, we'll talk at least about a few of them later, because we need it. But this expansion works. Now, what happens when you try to do, so non-renormalizable, the non-renormalizable case is when the coupling constant, non-renormalizable couplings are always called capital G. Non-renormalizable couplings are the ones where the scale dimension is less than 0. Example, let's say the scale dimension is equal to -2. Okay? Like G Fermi or G Newton. Then you're doing an expansion. So the dimensionless measure of what you're expanding in has to be made up by some energy or momentum scale in the problem. And so you're effectively doing this expansion. Okay. And that implies, of course, there are subtleties here too. And this expansion is very beautiful and a natural generalization of this expansion. This expansion. And it is in general called non-normalizable effective field theory. Now, but the question is, where did the word effect? Of course, there are many subtleties. They're exactly the same subtleties as here, with only a minor generalization. Again, you should learn it. But after all the subtleties come in, you're doing this expansion. And this expansion tells you why the word effective is there. Even this so-called non-normalizable theory can be renormalized in this expansion and produce loop-level predictive results. Predictive. So that's what I mean, it's useful. You do not just have to use non-normalizable theories only at tree level. You can use them at loop level. But after everything's done, since you're doing this expansion, it can only be valid for E less than 1 over square root of t. Okay, so that the expansion parameter is small. Otherwise, what could you have possibly been expanding? Hence, the word effective. Okay, so this corresponds. This is what we would normally call the weak coupling face of quantum field theory, and this is the weak coupling face of effective field theory. Okay, and the effective is because that's right. Okay, so there's one more concept to remind you of. Although the students sometimes you may not necessarily use this word, which is the idea of a UV completion. If somehow you find in nature that this kind of an expansion seems to be working in the regime of energies that you have access to, because presumably your energies are smaller than the scale, so this effective thing works pretty well, as it has a couple of times in history the low energy, strong interactions, pion physics had this. Of course, the Fermi theory worked rather well. That would appear to, in the pion case, the loop level expansion actually is interesting and useful even in the data. But this whole program works well at low energies, and yet it's the fact that it works, since it's true in nature, you'd say, what stops me from going to high energies? The theory might break down, but surely something takes place when I start scattering in energies or momentum transfers which are large compared to this scale. Something must happen. And so that something, whatever that is called a UV completion. Is theory is the renormalizable theory that the effective field theory approximates. At low energies. So we won't think of this theory as merely a low energy expansion, a low energy approximation of some theory which actually is renormalizable in the sense that it extends to a much higher energy scale. And how can we do that? How can we visualize doing that? That's a simple plot and you know it. We imagine that this effective coupling G is secretly of the form like this, that this is actually got negative mass dimension because it's secretly some dimensionless coupling. But there is some heavy mass that you are not able to produce. Your energies are not able to access this heavy mass. And that at high energies, as the energies go up, this really looks like this. If you want, you can throw in momentum. That secretly, this seemingly point-like exchange is the exchange of new heavy particles. And as soon as you do this, where the dimensionality of the coupling is 0 again, you say that I was tricked at low energies into thinking I had a non-renormalizable coupling. In fact, I had a renormalizable coupling, but the exchange of this heavy particle when the energies are low just looks like, effectively, a non-renormalizable coupling. So then, this is renormalizable again, and this is what we mean by U. It seems like a simple plot, and yet, in the case of G Fermi, and the W's and Z's with J equals 1, the story is certainly in this class, but subtler. If this particle, which shows up at high energies, was just a scalar particle, then the story would be pretty much as simple as I'm saying. However, the particle that ends up resolving the Fermi theory into a renormalizable theory is in fact subtler, and you know that it's subtler. Let's just quickly see in what sense. Okay. So let's throw away a lot of complexity and just do this example. I want to write an example in which there's a massive W, and all the interactions to your theorist's eye are straightforwardly looking very symmetric. Okay, so here is the Lagrange. So this is the massive W, 1, 2, 3. There's no Z, there's no photon, there's no graviton, there's just these 3 particles. So this is massive spin 1. Okay. And so the Lagrangian is just, I'm going to write G mu nu as opposed to F mu nu in a technical sense that I'll explain in a second. Because this is an interacting theory where G mu nu is equal to the usual epsilon. Epsilon is, if you like, the FABC when the group happens to be SU2. The structure constants of the group are the usual epsilon tensor in 3 dimensions. Okay, so what have I written? To an experimentalist, they would see, if they studied this theory, they would see the fact that these interactions look gauge invariant. In the sense of the finding rules and so on, you can't actually, you can pick apart these things. This does not look gauge invariant. So it is like, this is a cartoon of what the data really looks like. However, once I decide, and you can see that it's not gauge invariant off the top. But one thing I've done here is I've given, for simplicity and as well as because it is an approximate statement of the real world, we have not, I'm just doing a theoretical example, so forget the real world for a second. But I'm giving the same mass to W1, W2, and W3. As long as I'm messing up gauge invariance, how does it matter? I could make W1, W2, and W3 be not degenerate. But for simplicity and also for later use, I'm giving the same mass to these guys. So it's not gauge invariant, but there's an SO3, you want SU2 global symmetry. Okay? So, to the experimentalist or the person just classifying the states of the theory, there really is a degeneracy of SO3 in terms of the asymptotic states. So, let's consider this theory. And this forces us into, once you decide to break gauge invariance, why not break gauge invariance here? But I'm not going to. But we can question it, and we will question it later. This kind of question is not just a question that one asks theoretically, although we are taking that viewpoint. It's also the kind of question ultimately you can ask experimentally. You can imagine doing a lot of data and trying to figure out all the interaction vertices that come from this non-abelian term out of here. And you can try and say, is it really fitting that it all packages back into something that looks gauge invariant? Or is it not? And we can question the significance of that, and we are going to. But just to start the game, let's just take this as summarizing the data that in some imaginary world comes out to be just this, no fermions, no complications. So as we're thinking about this, we say, look, there's one coupling constant, and it's easy to work out that its dimension is 0. The gauge coupling has a dimensionality 0. So, naively, the general rules say it's going to be renormalizable, life is good, And this theory can be extrapolated to high energies. Okay, that's what it would appear to say. However, this is the summary of a certain amount of diagrammatic analysis, right? This is the executive summary. It's not a proof in itself. This is not a proof of anything. It's just a statement of the final result. Something new happens here from the diagrammatic point of view. Okay. The propagator, so the key feature of the diagrammatics is going to be the propagator. And the propagator has this form. Okay? So this is the standard spin 1 propagator for j equals 1, or you can just work it out from there. And this thing, normally for bosonic fields, when you're working out how the diagrammatics works and you're proving this result, normally you find that for P, or if you want P squared, for high virtuality, that the propagator falls off like 1 over P squared. That's normally the case, but here, because of this extra, so if that was just that, like some finely gauged photon or something, this would be true. But it's not because of this thing, okay? And it's this behavior at the diagrammatic level, all of this only has relevance by assuming this sort of standard fall off of the bosonic propagators. So that's dead now, okay? Instead, there is something that looks suspiciously like non-normalizability. If you look at diagrams, suppose you had some particle, I don't care whether this itself, suppose I exchange a W, okay? This itself could appear, since I only have W's in my theory. So let me focus on this exchange particle. There's going to be a G here and a G here. And one of the terms that you're going to get is this sort of P mu over MW squared. And then multiplied by what you would call a standard looking propagator. Okay? But this starts to look, it smells a little bit like a G squared over MW squared times some P squared. Okay. Energy over MW squared, G. It looks like a standard propagator, but with a kind of something else going on that looks like you're expanding in it looks like a little bit like this kind of expansion. Okay? So the question is whether this is secretly, is this a normalizable theory or a non-normalizable theory? But the fear from this pathological propagator is that there's secretly a non-normalizable G in the problem, which is given by G squared over MW squared. This MW here, for large P, becomes irrelevant. Masses become irrelevant at high energies. That's the usual statement. But here, it's not true. For high energies, this term is becoming more important, not less important. And so the usual statements we make to ourselves to pacify ourselves that at high energies masses are irrelevant are breaking down here. And they're breaking down in such a terrible way that you might worry that there is some sort of non-normalization. Now, you know at the end of the day that that is the case, but let's review the efficient way to zoom in on this pathology rather than, so we try and tackle it like this. diagrammatically, all the different things that might go wrong. We only suspect it right now, but bad things do happen. The theory secretly is not extendable to high energies. And, but what is the more efficient path to discovering this problem? And so that is called the Stuckelberg trick, or the first move in this discussion is called the Stuckelberg trick. So this is a question that we're asking here. It's puzzling. The usual game in normalizability is breaking it. Okay? So the Stuckelberg trick. I don't know if it's Berg or BERG. I don't know where all the thoughts are. Stuckelberg. Forget this theory. It's too hard. Okay? This is complicated. It's messy. Let's just consider a completely different theory. It has our non-abelian gauge invariant theory. Beautiful. Everything is good. Massless W boson. It's just non-abelian gauge theory. And now we're going to add some matter. And this matter field, the matter field transforms like this under gauge transformations. Where this can be thought of as a SU2 gauge transformation. Okay, so it's the classic matter field. It transforms by an SU2 gauge transformation, and therefore this whole theory is gauge invariant. Okay. Life is good. We think we understand it. It has massless W bosons in it, so it would seem. What's the next move? Oh, yes. So, two things to keep in mind. Hence, the covariant derivative looks like this. This is what I mean by the covariant derivative, obviously. The infinitesimal version of this is for a totally finite gauge transformation. The infinitesimal transformation is that follows by just writing omegas like this. Of course, SU2 group elements can be written as by exponentiating the Lie algebra. So infinitesimally, this is good. This is all totally standard textbook. We understand it perfectly well. Now, this is canonically normalized. There, I did it right. Here, yes. I'm going to change the wave function of the normalization by, how does that matter? You can always absorb, you can redefine sigma so that the V is inside the sigma and then it goes back to this standard normalization. Wave function of normalization is physically trivial. Again, theorists can choose the conventions for the normalization of a field. Okay. So I've chosen to put V there, and V is the weak scale. So purely for convenience, of course. It's the weak scale, which corresponds to MW over G. But you can just think of it as some bizarre choice of convention for the normalization of this field. Okay. And I'm duly dropping factors of 2 because I don't want to keep track of it. Okay, but so far it's a terribly standard non-abelian gauge theory. Nothing very subtle is going on. The first thing, which may be unfamiliar to you, but really is not any more complicated. It's no more, there's nothing strange about the next thing I'm going to say. It's just you haven't done that case maybe, or if you haven't done it in this language. Let sigma is a 2 by 2 matrix field. Okay. Normally, you think of fields phi, and then if you have several of them, you think of them as several of them, and then if you think of it in sort of vector notation, you think of it like phi 1, phi 2 as a column vector. But in fact, there's nothing wrong with talking about fields where it's phi 1, 1, phi 1, 2, phi 2, 1. There's nothing wrong with matrix fields. You're already used to vector fields. I mean, vector in some abstract space, right? This is just a bunch of scalars, Lorentz scalars, but it's just a matrix of scalars, okay? No big deal. This is not the problem. So far, I'm, again, still being very standard from the point of view of just doing non-abelian gauge field theory. If this was it, this is a nice renormalizable theory. If I add some potential for sigma, life is good. Okay. But this is what's called a constrained. It's a constraint. By the way, when I do a gauge transformation, I get something back of the same type. 2 by 2 matrix. 2 by 2 matrix times 2 by 2 matrix, another 2 by 2 matrix. So it seems that there's nothing wrong here. But I'm now going to say that the sigma has got a constrained form. And that constraint is that it has the form where these are real, unconstrained scalar fields. These are real fields. Totally, there's no constraint there, the usual kind of fields you're used to. But this thing is a special kind of 2 by 2 matrix. It's not a totally random 2 by 2 matrix. It's got this special form. In fact, this special form looks like this special form. So you know what this constraint is. I'm constraining it to lie inside this SU2 group. Logically, I want to distinguish. There is a gauge group. This thing belongs to the gauge group. So let me write it here, gauge. My field belongs to another SU2 shaped field space. The fields live in a, SU2 looks like a 3-sphere. So my fields take values on a 3-sphere. At every point in space, there is this 3-sphere, and the field looks like points. It's like a spin system, where you have some spin that sort of points in some direction, but pointing in some isospace, some different space from the real space at every point in space. And just to distinguish it, let me just call this the field space. So you should think that there is some field space, and gauge transformations move you around that field space. But logically, the fact that this SU2 and this SU2 are both SU2, just consider that a coincidence. That they happen to look the same. So therefore I'm distinguishing them. Okay. Now, this is something revolutionary from the standard viewpoint of doing field theory. Because normally, field space is equal to some sort of vector space. If I have two values of a field, normally I can add them and get another field. Okay? You can superimpose fields normally. If it's a fermionic field, the sum of two fermionic fields is another fermionic field. If it's a vector field, the sum of two vector fields is another vector field. If it's two scalar fields, the sum of two scalar fields is a vector field. If it's a matrix field, and there's no constraint, the sum of two 2x2 matrices is another 2x2 matrix of general form. But when you have this constraint, the sum of two such things as this is not another thing that looks like this. Check for yourself. We do multiply SU2 matrices and get SU2 matrices, but we don't add two SU2 matrices and get an SU2 matrix. Okay? So this is, because it's not a vector space where you can linearly superpose, this is called it's called a nonlinear field. And this sort of nonlinear field theory is a step past what is sort of standard, the first things that you study. Okay, it's nonlinear. This constraint is the first time that I'm saying something a little bizarre from the canonical non-abelian gauge theory. Let's take out all the pieces and play the game with massless gauge fields. This is the first time I deviate from it. Okay, but other than that, life is good. We have a gauge theory. But that means we also have gauge invariance. And remember, physically, to have a good initial value problem, we mean that gauge invariance tells us that the fields are not in one-to-one correspondence with physical configurations. Okay. That is, W, mu, and sigma are physically equivalent to W, mu, and sigma, where you do a gauge transformation on each of them. So, if I take the gauge transform W and sigma are describing the same physical field, which is really some geometric type statement, as this. So, of course, that's just standard. So we'd like to, as theorists, we'd like to gauge fix this. And there are many choices of gauge fixing and so on, but there's one that is particularly nice, given this nonlinear structure that we have. Even though this is logically a different, this is field space, this is a group that acts on field space. Okay? Normally there's a group that acts on field space, and there's some field space which is a vector space of some sort. Here, it's still true. SU2 group element multiplied by an SU2 group element is still an SU2 group element. So there is a gauge that we can choose, namely unitary gauge. And that is the one in which you choose I'm going to choose the gauge transformation, or which of these? Should I choose this pair or this pair to describe nature? Well, of course, there's an infinite number of these because there are an infinite number of omegas. I'm going to choose the omega such that this is true. Okay? And you can see that this is a beautifully unique one-to-one, it picks precisely one omega out of all of them. Given the original sigma, what we're saying is omega. So of course, the gauge transform of sigma is nothing but omega sigma. So the omega is totally fixed. This notion of group theoretic inverse makes sense because SU2, I can talk about the inverse. If it was totally a general field, the field could be zero. If the field is zero, then there's no way you can go around saying something like this. You can't do inverse of zero. But in this nonlinear theory of this type, we can. We can actually do this. Okay. So this is a clever gauge fixing because now the sigma in this new gauge, the sigma is gone. It's just turned into the identity maker. And so we can see that. So in unitary gauge, we just end up with okay, so what happens when I take this and I plug in sigma equals 1? Since sigma equals 1, its derivative is just gone. This thing just becomes 1. So the covariant derivative of sigma is just w, and I end up with w squared, g squared, v squared is nw squared, so you end up here. This is our old theory. So in other words, this particular gauging, this gauge theory with a nonlinear field can be gauge fixed, just a choice of gauge fixing, in a beautiful way, and gives us back our old theory. So that in disguise, this old theory that we started with gauge invariant looking interactions, but non-gauge invariant looking masses, secretly the entire theory can be recast as gauge invariant. In that sense, it's still a theory of some sort of quantum geometry. But in disguise. Okay? And okay, so you know the usual textbook words. Let me just say it again. That the in this form, it looks like there are these degrees of freedom. It looks like the pi a are some degrees of freedom in my Lagrangian to the theorist I. But by gauge fixing, I get rid of the pi degrees of freedom. In this form, it looks like the W boson might be massless. Again, superficially, it looks like it's massless. It's non-Abelian gauge theory. Here, it looks like it's massive. Okay, so we say that the W going from this line to this line, which is just an observation, it's a passive observation, just a gauge fixing. We say that the W has eaten, these are all theorist words, but they're taken out of the textbooks. The W has eaten the pi's and gained weight in mass. It hasn't gained anything. This theory, if I studied it more carefully, would have been this theory, and they're just the same theory. Just one is a gauge fixed version of the other. Okay. So, this is the standard statement. Indeed, this theory, if we want to study it in terms of renormalizability and so on, looks like we have to study the complicated looking propagator and so on here. The trick is to study this theory instead. They are the same theory. This is just a gauge fixing. Let's look at other gauge fixings of this theory. So, in a general gauge, I don't have this. I'm still looking at this. And we can consider, so this gauge, I don't care what sigma you started with, I'm going to gauge fix so that the sigma is just the identity. Okay? But in a general gauge, sigma doesn't have to be the identity. But we have to expand around some ground state. Okay? So let's consider that since I lived in a symmetric space, this field space is symmetric, which direction I say the ground state is pointed is irrelevant. I might as well take it to be the identity. So this is a different reason for saying it. I'm not saying that in a general gauge, sigma is not constrained to be the identity, but its ground state might as well be taken to be the identity. Okay? In which case, but now I want to look at fluctuations around this ground state, which is where the pi's gain lie. So if I look at this d sigma squared, we see that it contains, so I'm just expanding. The sigma is written as exponential of pi's. If I work for small fluctuations of the pi's, then you'll see terms that look like this. And therefore, it contains things that look like d mu pi squared, and g squared, w squared. This is there, even in the unitary gauge, we have this term, but we'll have fluctuations that look like this, but we'll also have this, being sloppy about all numbers, we'll also have things that look like this. So even at the quadratic order of just studying the free field kinetic term for the pi's and the w's, we see that there is mixing, right? I'm doing quadratic order as if there are no interactions, supposedly. But we already see in this funny nonlinear theory that there is mixing of the degrees of freedom. It's as if in a scalar field theory I wrote d phi 1 and then d mu phi 2, as well as d mu phi 1, d mu phi 1, and d mu phi 2, d mu phi 2. If somebody gave you A, B, C, the obvious thing is please diagonalize this matrix of kinetic terms. Let's rotate the phi's and rescale the phi so that we get rid of this and we get 1 and 1 and get everything back canonical. At quadratic level, there's no excuse for not making everything look canonical, right? So in a general gauge, even if I take the ground state to look simple, there will be fluctuations, and then I'm stuck looking at ugly things like this. So let us choose a gauge which makes the theory look more renormalizable, that is more susceptible to the standard diagrammatic techniques that give us power counting and all of that, and tells us that the theory is renormalizable. At least we can try and check it's renormalizable. And as well, let's try and clean up this ugly mixing of degrees of freedom, even at quadratic order in the action. Okay? So there is a beautiful class of gauges which does that. And those are the RC gauges. This C is the parameter of these gauges. And so the gauge fixing term, in these things is so at first sight, it looks nicely like one of those sort of things that looks like a Feynman gauge fixing term type thing. d mu w mu u squared. This is what we're used to. Life is always good. But there's a trick here to try and kill this cross term, which is to put in, and this is some sort of gauge fixing parameter as usual, but we can put in mw okay. That's the trick. Because now the cross term here, when you expand this out, you add this gauge fixing term to your Lagrangian, the cross term, the C cancels in the cross term. But you see the cross term here can be chosen to precise, there's some sign in fact which is here. The cross term can be made to cancel this term. By integration by parts, this d mu could be there. And so that's what's nice about this. Okay, so that thing will knock this off. At least we've done the usual thing that a canonical person does, which is to clean up the kinetic term to at least look diagonal in field space. Okay. But it has another feature, at least naively we can see it right here, which is that for, which one is it? C goes to infinity. For C goes to infinity, this term is the only one that's important, because this thing goes like C squared, which beats the 1 over C. Okay? For C goes to infinity, you're just getting that's it. In fact, if C goes to infinity, it looks like the pion is becoming infinitely massive. And if it's infinitely massive, then we can throw it away. We cannot activate this in any scattering amplitude. It's infinitely heavy. In that case, it's not just the ground state that's the identity. If we shut off the pions, these pi's, sigma is the identity matrix. So that gauge fixing is precisely the limit that you go to unitary gauge. Okay. So at one end of the spectrum of RC gauges is sitting our old friend, the unitary gauge. But then there are other gauges in which it's, in other words, it's any finite C, it's not unitary gauge. In fact, let's just quickly write down what the propagators are. Find the rules. So I'll just write it. This is so the W propagator looks like a standard scalar propagator, but so as P goes to infinity, this does in fact behave like 1 over P squared. Okay. For finite C, this is like standard gauges, where in fact the good power counting at high energies of boson propagators go like 1 over P squared. That's still happening. Okay, that's the beauty of these gauges. But there is the price to pay is that there are these pion degrees of freedom, these pi's. That's all I mean by the word pion. And they have a propagator which looks like P squared minus C and W squared. That's why I said it looks just like a particle of mass squared C and W squared. C goes to infinity, it's infinitely massive, you can forget about it. Okay. Integrate it out of the theory results. Okay. And in fact, there is this gauge fixing, unlike the purely unitary limit, this gauge fixing does have ghosts. Okay. study of non-abelian gauge theories. At some point, gauge fixing requires this ghost determinant, and the ghost propagator is also got. There's a massive ghost. Again, the ghosts disappear. This is C. If C goes to infinity, then even the ghosts are massive, and I can forget about it. But this looks like standard business in renormalizable non-abelian gauge theory. All the propagators behave well, etc., and renormalizability So all of this good stuff of non-abelian gauge theory tells you that you have in fact restored the renormalizability of the gauge interactions. Life is good because all of the usual reasoning tells you that the gauge interactions are renormalizable and extendable to high energies. But there is trouble because it's not the only kind of interaction in town. There are other interactions that are now hidden. And these interactions are, you see, whenever you say that the superposition principle is true, if I can add an electromagnetic wave going this way with an electromagnetic wave going this way and get some new electromagnetic field, why can I do that? It's because the two electromagnetic fields don't interact with each other, they pass right through each other. The superposition of waves, or the superposition of fields, is equal to the statement that the fields are free. Okay? That they don't interact. As soon as there is interaction between fields, then you cannot just say, here's a solution to the equation of motion, here's another solution to the equation of motion, add them, I get another solution. That's not true. But we know that this theory, where all this renormalizability works out for the gauge interactions, we know that this theory contains a nonlinear field, sigma. The sigma degree of freedom is not dead, it's sitting there. And we know that sigma, if I have some solution to the equations of motion for sigma, I cannot just add it to some other solution to the equations of motion for sigma and get a new solution. Because sigma space, the field space, is not a vector space, it can't even act. So you should automatically smell the fact that this is not, there must be some secret nature of coupling that is hidden in the fact that I cannot just add sigma fields, okay? There's absolutely no ability to add sigma fields. That must mean that there is some sort of interaction lurking there. And now we have to ask whether those interactions are renormalizable. Okay? The problem has been shifted in this choice of gauges from the original unitary gauge, where it looks like there's at least a question of renormalizability because the propagator behaves so differently from the propagators of bosons for which the standard theory of diagrammatic analysis holds. And now we're in a situation where we got all of that to work out, but secretly we suspect that there are some other interactions lurking, and we have to ask whether they are normalizable or not. Okay, so that's our answer. Okay, how can we focus on those? Let's look at this. So, this G, we're trying to do non-abelian gauge theory. There's some gauge coupling. We're of course saying that it's small so that we can imagine doing perturbation theory in it. If it's so small, we're not worried about it. We're not even worried about extrapolating it to high energies. All the propagators look good, everything looks good. If it's so small and we cannot worry about it, let's drop it. This is not our problem. Okay. in that case, our Lagrangian we don't even have all the subtleties of gauge. As soon as I drop the gauge coupling, the W particle has completely decoupled from the sigma field. They don't talk to each other. So I can throw away all the W's. Those are just a bunch of free photons. Who cares? But that still leaves this, where there's no more covariant derivative, because I've thrown away this G equals 0. Okay, I'll drop it. Instead, we analyze this theory. Okay, and we're trying to ask, I'm trying to zoom in, where are the interactions? If there's some trouble here, then it must be coming from this part, the nonlinear field. If this was a linear field, this would actually be a free field, and there would be no trouble at all. We'd be very happy. But it's a nonlinear field, and we need to analyze it. What are we concerned about? Our focus on potential strong couplings we're worried about strong couplings where perturbation theory is going to break down in some way and our control of the theory breaks down, especially as concerns extrapolating to very high energies. So if this thing contains couplings like that, then it is consistent to throw away the weak couplings and just focus on the strong ones. Okay? Indeed, that is going to be the case. This is a self-consistent analysis of this. And you can see why, because the sigma, remember, has got things like look like e to pi a, tau a. By the way, sometimes I write V like this and like this, and of course it's the same thing. In fact, you can see why we chose this funny normalization here, given this, because if you expand this out in the unconstrained field, pi, then in fact you get canonical normalization. Because the 1 over V here cancels these V's, and you get this. However, you now start to see new terms that look like this. If I keep expanding, indeed, I see that there are real interaction. Once I'm down to unconstrained fields, we know how to think about it. These pi's can be superposed. Because they're unconstrained, they live in a vector space of triplets. Okay? R cubed is the vector space of these pi's. But now indeed we're seeing interactions. Okay? And the interactions actually do have 1 over V squared, which is, if you like, G squared over MW squared. So we were right in what we suspected in unitary gauge as being true, that secretly there are interactions which are non-normalizable, and we're seeing them. And it was in fact self-consistent to throw away this G, because at high energies, the expansion in 1 over V squared is an expansion in E squared over V squared. The dimensionless strength of these couplings goes like this. At high energies, this becomes large, and larger than any G that we think of as parametrically small. And so it was in fact consistent to throw away these couplings, which were perfectly well behaved, even in the ultraviolet. And so this is a problem. This is the face of the problem that we're facing, okay? And this whole Stuckelberg trick, etc., has allowed us to take the problem of non-normalizability in the unfamiliar language of massive spin 1 propagators and put it in the familiar language of scalar field theory but with non-normalizable couplings. See, it looks like 5 and 4 couplings, but it's got extra derivatives. So this is actually a non-normalizable coupling. It's a dimension 6 operator. Pi has dimension 1, 1, derivative is 1, and it's all squared. So it's a dimension 6 operator divided by v squared. Okay, so that's the beauty of this analysis. So now we see who the true villain in our story is. It's these degrees of freedom. And so this approximation, so dropping it, so now we know that it's not potential. There really are strong interactions. And the strong couplings are strong, that is, it's consistent to drop the G once the E is bigger, so E over V should be bigger than G. Okay? Then it's consistent to drop the G. That's otherwise known as E is bigger than GB, and that's otherwise known as E is bigger than MW. So at energies higher than MW, it is consistent to completely neglect these gauge couplings and just focus on the bare face of this analysis, which is just scalar fields. And indeed, our question is, can we extrapolate to energies above the W mass? Below the W mass, there's no W to work. Okay. This analysis, which says that at high enough energies, to a good approximation, the most strongly interacting pieces of this gauge theory, or the theory of W bosons, the unitary gauge, which is what the experimentalist sees, that the strongest pieces of those can be treated as a bunch of spin zero particles with self-interactions. That is the basis for, so this sort of, the moral of this analysis has a technical face, which is what's called the equivalence theory in the literature. Okay? Okay. So it says that once we get to these energies above MW, that we can start to think in terms of these degrees of freedom, and we see that we are facing non-normalizability, and we don't have a plan. Okay? So what can we do? So in fact, I've given you the rationale for dropping the gauge coupling, but when I drop the gauge coupling, I actually don't have any gauge symmetry, but I actually do have some global symmetries. Okay. What are the global symmetries of this theory? It's an incredibly simple theory. What are the global symmetries here? And global symmetries. By the way, this theory is called a nonlinear sigma model. It's the classic example, the nonlinear I've explained to you, and it's called a sigma model because somewhere along the line they must have called it sigma. Okay? This is the nonlinear sigma model, and we want to know what are its global symmetries. This is just the simplest example of a nonlinear sigma model. Many nonlinear sigma models, but this is one. In fact, you can see it right up there, which is, I should have said what I meant by this, which is that every term is being squared, but let me say it in matrix language, that the Lagrangian is b squared, and it's d, so let me write it out a little more carefully. 2 by 2 matrix, so I'm actually daggering it rather than just complex conjugating it. And to get some Lagrangian, I'm taking tricks. If I covariantize these derivatives, then you can check that this is in fact gauge invariant. Maybe I should have said that earlier, but I was writing in a very compact form, but this is actually what I mean. Okay? The 2 by 2 trace of all of this. And it starts life like this. So then that would be gauge. But because of this, it's easy to see that this is invariant under this. It's actually invariant under two SU2 symmetries, where L is an element of SU2, of one type of SU2 that acts on the left, that's the word SU2 left, and the other is another SU2, sorry, by convention we put a dagger there, is another SU2 matrix. The dagger, of course, is the same as inverse. Another SU2 matrix, or another SU2 group, which is distinct from this SU2 group, one which acts on the left, one which acts on the right, because of this trace formula and the fact that I'm only talking about global symmetries. This is obvious. We gauged this. And now we're throwing away that gauge interaction. So previously we had gauged this. We had not used this in any way in that example. We could, but we didn't. And so this is symmetry. And this ground state you might say, why didn't you choose this ground state? Why didn't you choose the ground state that we usually think of as the simplest thing, 0? And the answer is because I have a constraint which says that sigma is a unitary matrix. So this is not even available to me. The best I can choose as a ground state, in fact, given the symmetry, the most general choice, and then I readjust my field coordinates, is pi equals 0. Pi equals 0 is this. So without loss of generality, this is sort of the most general ground state I could contemplate. And you can see that this breaks SU2 left cross SU2 right. Okay, if I put the identity here, the identity is not invariant under this because the identity goes to LR dagger. However, it breaks it to SU2, what's called diagonal. It's the diagonal, it's the subgroup of SU2 cross SU2 such that L equals R. Okay. If I constrain the group elements to be the same here and here, then that is a symmetry. It's also, in the Electroweak context, called custodial, for reasons that we'll talk about later. Or maybe I'll say it right now. There's an SU2 custodial that is not broken. It's not surprising. Everything started from choosing m squared I chose an SU2 symmetric mass. I chose W1, W2, W3 to be degenerate at the start of my story. I didn't have to, because I'm already breaking the age invariance. Who cares what I do? I did choose that, and so my starting theory to the experimentalist, I'm not talking about some theorist symmetry, the experimentalist would directly see the Lagrangian I wrote down at the very beginning, the unitary gauge Lagrangian. The experimentalist would see a spectrum and interactions which completely respected a global SU2 symmetry. So right from the start, I have put in a global SU2 symmetry as my starting point. It's not surprising that after all the theoretical manipulations, that I have a global SU2 symmetry that is no way broken in any subtle way. It's just there. All the states will be classified in some way under this symmetry, even when I go to this funny limit, very nuanced limit, because these ions are not in the space. The experimentalist does not see scalars. He only sees massive spin 1. But in this funny theoretical analysis, it's still true that the symmetry SU2, overall SU2, is going for the ride, it's still there. it's still preserved. But these more theoretical SU2s, funny things in this analysis, Rubenberg, blah, blah, blah. Those are being broken in this way because of this choice of ground state. And I have no choice but to choose this ground state because I have a nonlinear field which has to point somewhere in matrix space. Okay. So this is of course nothing but spontaneous symmetry breaking, where a vev of a field breaks some symmetries and you get a lesser symmetry. The lesser symmetry is very obvious to the experimentalist. It is realized in the world in terms of the degeneracies of states and the relationship between reaction rates. Okay, it's the most obvious manifest way. And so we see that here. In that sense, because it's spontaneous symmetry breaking, and in this limit, we have only global symmetries. The Goldstone bosons, the spontaneous symmetry breaking implies Goldstone bosons. And these are precisely what the pi A's are. This nonlinear field automatically forces spontaneous symmetry breaking to happen. And it also contains the Goldstone bosons, which are mandated by spontaneous symmetry breaking and Goldstone symmetry. Okay. So all in the one handy package. And so in the eating, we say the W eats Goldstone bosons. I emphasize that there is an experimental phase. It sounds like the words of a theorist, because we say, look, there's no scalars in the spectrum, blah, blah, blah. But there really is a sense that when you study the experiments, I mean, if you imagine doing the experiments, that once you get to energies above MW, if you start, the experimentalists can see where the strong interactions are taking place. And if you filter everything, throw away anything that's a weak interaction, you just look at the stronger interactions, you will see this physics. So you will literally see these Goldstone bosons in that sense. You can strip off the Goldstone, just in the same sense that we see partons when we smash protons together. The end states are really only protons. But there is some real sense that the experimentalist has that they are, in the data, seeing the parton scattering. Similarly, there is a sense that, experimental sense, that these pi's are visible experimentally once you're in the right region. Okay? And so there's giving a kind of physical sense to these words, eats, also both. Okay, I think I started at 10 past, 10 minutes late. This is called the Higgs mechanism. Which is a kind of theoretical statement, okay? But the physical face of the Higgs mechanism is that you can do this experiment, this class of experiments, and see the growth of this, okay? In the real world, you have to get to energies substantially above the weak scale, and this is an interesting thing. We'll talk a little bit about it later, but this is an interesting thing to do, which in a sense has not been done in its classic form yet. We're not even at that energy in that sense yet. But it's a beautiful general feature. But this is the Higgs mechanism, but this mechanism does not equal the Higgs boson. The Higgs boson, as you know, is a massless, is a spin zero particle, and it is truly spin zero to the experimentalist, not just in some funny theoretical way of talking. And I never mentioned it, and so we are stuck so far. Maybe that's what this is stuck. We're stuck saying, what is the role of this? So we have one problem, And one thing that you guys, of course, know is the solution, because you know too much now. But the problem is the non-normalizability of the nonlinear sigma model, and the solution is going to be the Higgs boson. Okay? Basically, we are going to choose the Higgs boson as a way of softening the constraint. The constraint that sigma should be living on a group surface. Instead of making that a hardwired fact, I insist that sigma be living on the surface of the group manifold SU2. We are going to make it instead the solution to some equations of motion, where sigma can do whatever it wants. But dynamically, it finds it relaxes to live preferably on the surface of the SU2 manifold. But if you kick it hard enough, it will go off that constraint. And that will give us the renormalizable theory rather than this non-normalizable theory. But the pushing it away from the constraint will be the Higgs boson. Okay? So let's do that 2 o'clock.
Yeah, before I